Good morning, everyone. So I can see people are still joining, but we have started the recording. So this recording will be made available afterwards. So anyone who arrives a little bit later, they'll be able to watch back this initial start of the webinar later. So thank you so much for joining us today to this Vulnerability Modelers Toolkit webinar. As you will have seen, this is a joint webinar that is being hosted by both EFEHR, the European Facilities for Earthquake Hazard and Risk, and by the GEM Foundation. We do have an agenda, as you can see here on the screen. We're going to be quite flexible about this agenda, but the plan is to spend the first half of this webinar focusing on basic users of this toolkit, running through some of the background scientific features of the toolkit, how you use it with its graphical user interface. We'll talk a little bit about how to install that on Mac and Windows. And then we will run through an application example of how to use the user interface version of the toolkit. We're here and available to answer your questions. There is a Q&A box, so please use that to write your questions in rather than the chat. And we will either answer those questions by typing responses, or we'll answer them live if there's something that we can show you that will help us in responding to the questions. And then if there's time, we have a short break, and then we have the second session of the workshop where we will be presenting the toolkit more from an advanced user's perspective. So people who are more familiar with Python coding and want to maybe modify the code. And we will look at the GitHub repository, and we'll give you some examples of how you might modify the code for your needs. And then finally, we will have a presentation on the future plans of vulnerability modeling that GEM is planning. So this workshop, we have 4 speakers, myself, Helen Crowley from the EU Centre. The EU Centre is running the risk services of the EFEHR, the European Seismic Risk Services. And then we have 3 colleagues from GEM. We have Martina Caruso, who is a new employee of GEM. And we asked her to present because she actually used the Vulnerability Modelers Toolkit before she joined GEM. And so she's going to talk about one of the applications that she used of the toolkit. And then afterwards, the main author of this toolkit, Luis Martins from GEM Foundation, will be presenting, and finally Vita Silva, the coordinator of the risk activities at GEM, will be talking, as I said, about those future plans. So let's get started. Oh, I'm just going to put on a laser pen. There we go. So this first presentation, I'll be giving an introduction to GEM's Vulnerability Modelers Toolkit. Before I do, I just wanted to introduce the 2 organizations that are hosting, just in case you aren't familiar with EFEHR or GEM Foundation. So EFEHR stands for European Facilities for Earthquake Hazard and Risk. It is a non-profit consortium of organizations that have a similar goal, that being to provide access to open data and models for seismic hazard and risk assessment at the European scale. EFEHR maintains the European Seismic Hazard Model 2020, which was released a couple of years ago, and also the European Seismic Risk Model that are available at these links that you see here. And we organize a number of working groups. We have a working group specifically running right now on testing of hazard and risk models, but also scientific webinars such as this event today and training events. We haven't specifically called today's event a training event because you are not working with us to use the tool, but we do hope that if you do use the tool in the future, you can watch back this video, and it can also be used, therefore, as training material. GEM, the Global Earthquake Model, is a non-profit public-private partnership. It's driving a global collaborative effort to develop scientific and high-quality resources for transparent, open assessment of earthquake risk, and to facilitate and promote the application of those tools for risk management around the globe. Now, just one second, I'm going to turn. I need to just reduce the video here so I can see my slides. Okay. So why is EFEHR organizing a scientific workshop on the Vulnerability Modelers Toolkit? It's because we use this toolkit for the European Seismic Risk Model 2020. So we had a number of capacity curves for hundreds of different European building classes, and we needed to produce vulnerability functions for those building classes. So we used the toolkit together with a set of strong motion records, European motion records from the engineering strong motion database that INGV maintains, and we produced vulnerability models for both economic loss, so considering the repair costs of buildings, the damage from earthquakes, but also for fatalities. We made use not of the GUI, the graphical user interface that I'm going to focus on now, but we made use of the source code, the open source code. And we made some modifications, and we have certain assumptions, all of which we've made publicly available on this GitLab repository. I think if you search GitLab EFEHR, you will find it quite easily, and you just navigate to the vulnerability folder there, and you'll be able to see exactly the scripts that we use, how we modified them, and the assumptions that we made. So whilst using this tool, we felt that it was a tool that more people should know about. So we felt that we needed to organize this workshop, this webinar, to get the tool more widely used, because we think it will be of great use to a lot of people that need to develop vulnerability functions, who have capacity curves, maybe have records, but don't have the means to produce fragility and vulnerability functions. So the objectives of this webinar is to explain initially the rationale behind the development of this toolkit, the workflow, and the main scientific features. As I said, we'll show you an example. We'll give you a brief tour of the repository where you can find the open source code and explain some of those main scripts that could be modified. And then finally present a summary of future vulnerability modeling plans at GEM. And we're here to answer your questions. And as I've said, please use the Q&A box to write your questions. As you know, we are recording this webinar, so you can hopefully come back and watch it again when you try the Vulnerability Modelers Toolkit for yourself in the future. So before I go any further, I want to make sure that we define and we're clear about what we mean by vulnerability. Vulnerability can take on different meanings and different contexts, but for the purposes of seismic risk assessment within the context of regional risk assessment that the GEM Foundation does and the EFEHR has done for its European seismic risk model, we're using vulnerability models that are defined as the probability of loss conditional on levels of intensity. And in our case, the intensity that we're interested in is strong ground shaking from earthquakes. So these vulnerability models are defined by mean loss ratios, conditional on the value of intensity measure. The loss ratio is the ratio of the loss to, it could be the value of the buildings in the case of economic losses, or it could be the ratio of the fatalities to the number of people inside the buildings for the case of loss of life. So we need to give that mean loss ratio, but we also have a distribution to model the variability of the loss. And this is defined by a type of distribution. It may be a beta distribution, a log normal distribution, and a standard deviation, or we, in the format that we define, is that we give the coefficient of variation. So how are vulnerability models produced? There are many different methods that have been proposed and applied by researchers to produce vulnerability models. And the Vulnerability Modelers Toolkit has chosen a specific workflow and a specific number of assumptions on how to produce vulnerability models. And so I'm just going to run through those. The reason being, as I said before, that the focus is on regional seismic risk assessment. So there are cases where you want to produce vulnerability model for a specific site or a specific building, and you may use very detailed models of those single buildings. But in other cases, you're looking at a very large area, a regional area, and rather than modeling every single building individually, you need to group those buildings into building classes. And so the Vulnerability Models Toolkit is focused more on modeling buildings in a simplified manner, grouping buildings into classes of buildings and representing those classes of buildings. Vulnerability models can be modeled through an analytical or numerical approach, where we attempt to model the response of the buildings numerically. or through empirical approaches, where instead we're collecting past damage data, past loss data, and we're relating that data to the ground shaking or the level of intensity. Both methods have their pros and cons. The Vulnerability Modelers Toolkit uses an analytical approach. We can control more the different building classes that we're covering, perhaps building classes that haven't experienced losses in the past. We can control the ground shaking. We know exactly the level of ground shaking that we're putting in our analyses, whereas when we have past empirical data, we often don't know the level of ground shaking that past buildings were subjected to. But often it's useful, once we have analytical vulnerability models, to still use empirical data to calibrate and validate. So the Vulnerability Modelers Toolkit uses an analytical approach. There's a balance between whether we want to model our building classes with a few multi-degree of freedom systems, very detailed models, and model the buildings with a lot of modeling detail. But in that case, often we can only run a few analyses. It can take a lot of time to build those models, to run those models. And so the other approach is to use a simplified single degree of freedom route, where we simplify the buildings classes down to single degree of freedom systems. This allows us to run many, many analyses and to explore different assumptions, different modeling choices. So the default of the Vulnerability Modelers Toolkit is to use single degree of freedom systems. But as we will present later, Luis will present later, as this is an open source code, it can be adapted to instead be used with multi-degree of freedom systems and a few more detailed models. And I think Vita might also bring up later, there is maybe a balance between having few multi-degree of freedom systems or many single degree of freedom systems. We can perhaps have another modeling choice, which we'll talk about later, which is in between these two. Static versus dynamic analysis. In the first years of development of vulnerability models, the approach was very much to use a static approach, to use a static nonlinear method, which aims to estimate the response of the buildings to ground shaking by a pushover analysis of the building. These methods were calibrated using a large number of dynamic analyses, but it's quite quick now to run dynamic analysis, especially when we have the single degree of freedom approach. And so the Vulnerability Models Toolkit goes straight to running dynamic analysis of single degree of freedom systems, rather than using a static approach that has been calibrated on dynamic analyses. Once you have run dynamic analysis of many single degree of freedom systems, there's different ways that you can use to calculate the probability of exceeding damage for your fragility assessment. And there's incremental dynamic analysis. You can use a cloud approach, multiple stripe. There's various methods that can be used. And in the default of the toolkit, the cloud method is used. But we note again, it's open source code. It can be easily modified to consider, for example, multi-degree of freedom systems, different assumptions on hysteretic properties, and also different nonlinear response methods. And Luis will touch more on this later. So potentially repeating myself a little bit, but I just want to make it clear what are the main concepts of the Vulnerability Modelers Toolkit. We have our single degree of freedom systems. We're representing those by what we call capacity curves. So these capacity curves are spectral acceleration versus spectral displacement response to the building. We take the single degree of freedom system. We run many nonlinear dynamic analyses for records with increasing levels of ground shaking intensity. We estimate the response of our single degree of freedom system to those different records, and we plot this cloud of data. So on the x-axis, this is the terminologies that are often used is intensity measure levels, IMLs. And so these are coming from the records. We might be picking up the PGA, the peak ground acceleration, the PGV, the spectral acceleration at different periods, the average spectral acceleration. This is coming from our records, and we're plotting it against the response of our single degree of freedom system. So for example, the displacement response of that building, the language here, and what you'll see on the tool, you'll see EDPs, engineering demand parameters, This could be displacements, it could be accelerations. And so the data is plotted and a linear regression is carried out. So this is the cloud and the linear regression is carried out by the tool. The next step that's needed is to define our damage thresholds. At what point do we reach different damage states in our single degree of freedom system? So from the capacity curve, we can define, for example, different displacement limits at which different damage states are reached. So in this case, we may have no damage up to a given point, slight damage, extensive damage, moderate damage, extensive damage, and then after a final point, complete near collapse or collapse. So once we have defined those thresholds, what the tool will do is it will apply those thresholds to the cloud, to the regression, and calculate the probability of exceeding those thresholds, given that response data, that linear regression. And that's how we build up the fragility functions. So the fragility functions tell us the probability of exceeding the different damage thresholds that we've given for our specific single degree of freedom system under those set of records that we've applied. And then in order to reach our final vulnerability models, which as I presented earlier are the probability of loss conditional on the intensity, we need to apply what we call in the tool a conversion model. Now we might be converting the damage states to loss, in which case for each damage state, we need a loss ratio. That's the ratio of, for example, cost of repair to cost of replacement, or it could be a loss ratio, a fatality ratio of a number of fatalities to number of people. Conversion models can also go directly from the response data to the loss, as I'll show you a bit later. So the steps of the Vulnerability Modelers Toolkit are all described in this paper, which has been published in the Bulletin of Earthquake Engineering. We have the link here. Luis is the main author of this paper, and the tool has been divided up into 7 main steps, at least the graphical user interface default version of the tool. And so I'm going to run through each of these 7 steps now to show you a few of the main features, a few of the main assumptions in this default version of the tool. And then afterwards, Martina will show you an actual live example of the tool being run. So the first step is the demand module. So this is about selecting the records that we're going to use for dynamic analysis. The second step is about providing the capacity curves of our single degree of freedom systems. The third step runs the structural response. So that's where the cloud, the nonlinear dynamic analysis is being carried out, and we're getting that cloud of data response for all of the records. The fourth step applies the damage thresholds and calculates the fragility functions, so the probabilities of exceeding different thresholds. The fifth step converts either the structural response or the fragility into losses. So you need to apply a consequence, or as I said earlier, a conversion model. The next 2 steps are just steps for helping you to understand better your models. You may want to compare them with other models that are in the literature. You may want to compare them with GEM's own models. And finally, there's a step to allow you to verify the models, to use them actually in application. So you can actually produce average annual risk metrics to get a better idea of how these models that you've produced are performing. So this is what the tool looks like. And this is the first module. So as you can see, we have those 7 different steps, and you just run through each step one by one. So starting, as I say, with the demand, which is all about selecting the records. So the user provides a database of records. Now, on the repository, we do have already a database of records coming from the Engineering Strong Motion database, which you can use, but you can also download your own records from other places and use them. So an initial database of records does need to be provided by the user. Now, the first option is that you use the records as they are in your analysis, in your cloud analysis, because perhaps you've already selected those records with other tools and you know that they meet the criteria, they meet the range of intensity measures that you want, they meet certain, perhaps they're condition, they are consistent with the hazard of your site. Alternatively, you can actually use the tool to produce a subset of records from that database that you want to use for your vulnerability analysis. So in order to produce a subset of tools, you need to, of records, you need to tell the tool what is the intensity measure type that it should be considering when looking through those records. So perhaps it's a PGA, perhaps it's spectral acceleration at a given period. And then you need to give target intensity measure bins. So in this example here, we have said that we want to a subset of records from our database where we're looking at the PGA, and in the first bin between 0 and 0.05 G, we want to select 20 records, and we can select we can scale the records, but only within a minimum scaling factor of 0.5 and a maximum scaling factor of 2. And so the tool will look at the database and provide you with those 20 records for each of those bins according to the criteria. There are a predefined list of intensity measures in the default graphical user interface version of the toolkit. Now, if you want to go and use other intensity measure types, this is where you'd have to be more of an advanced user and to modify the code itself. But in the toolkit, there are, as we'll see later, a selection of spectral ordinates, so PGA, spectral acceleration at different periods of vibration. The third option is that you actually condition your records on some characteristics of the hazard, and this is using the conditional spectrum method. The code itself is taking an algorithm from Baker and Lee. It's using the a conversion of their MATLAB code. It's been converted into Python and is available in this tool. So in addition to all of the other inputs I just mentioned before, so what is your intensity measure type? What are the target intensity measure levels? And how many records do you want? You also need to provide a hazard disaggregation file. Now, this is compatible with the OpenQuake engine format. So we have made it so that you can run the OpenQuake engine, you can get your disaggregation file and upload it directly here for the purposes of selecting records that are consistent with your hazard. Finally, there's a part at the bottom of that first screen on the demand module, which allows you to plot the spectra of the records. If you just want to have a look at them, make sure that they are meeting the criteria that you have provided. So you need to provide a minimum and a maximum period over which to plot the spectrum and the number of steps within which to break that up, and it will plot the spectra for you. So that's the first module. The second is the capacity module. So this is where we're providing our capacity curves of our single degree of freedom systems. And here again, we have various choices that the user can make. One thing that the user needs to consider is that you can only provide a capacity curve in the user interface as either a bilinear, a trilinear, or a quadrilinear backbone. So as you can see in this example here, this would be a quadrilinear backbone. If I stopped it here, it would be trilinear. If I stopped it here, it would be bilinear. As I mentioned before, in terms of spectral acceleration versus spectral displacement. So the three options are: the user inputs the capacity curve directly in the graphical user interface. So with this first option here, they would choose the type of model and directly put in values separated by commas of the spectral displacement values versus the spectral acceleration values. If instead you already have your capacity curves in CSV files, or if you're dealing with more than one building class, you may want to use the other options. So you could input a single or multiple capacity curves for a single building class, or you could input single or multiple capacity curves for multiple building classes. So here I'm showing an example of multiple capacity curves for a single building class. So this might be, for example, reinforced concrete, two-story moment frame. And this is the 100 different capacity curves to take into account the building to building variability, the geometrical properties, material property variability. Instead, I could have just a single capacity curve, but I have multiple building classes. So here I'm looking at 6 different numbers of stories of a given type of building, and I can input all of those building classes in one go. The uploaded capacity curves need to be uploaded as CSV files. You need a separate CSV file for each building class. And it's a very simple format with a single column of spectral displacements and another column of spectral accelerations. And the displacements need to be in meters and the spectral acceleration in G. If I have the multiple versions, so if I'm providing multiple capacity curves for a single building class, then I need to repeat those pairs of columns many times. So that we've provided our records, we've selected them, maybe a subset of them. We've given the tool the capacity curve that we're interested in. Now we get to the part where we're going to actually run the dynamic analysis and get the response of that single degree of freedom system. So the tool is using OpenSea's Pi to produce the nonlinear response of each backbone curve that we've provided to each record. The default in the tool is to use the pinching for hysteretic model. And the user just has a choice of whether or not to include degradation. So here, degradation, you can include or not energy degradation in that hysteretic model. Mass proportional Rayleigh damping is the default assumption, and the user just needs to provide the damping ratio for each of the building classes for which they've provided the capacity curves. So then once that input has been provided, the analyses are run, the user waits for the analyses to be completed. You can run the nonlinear response for a single building class, or you could choose to run them all at the same time. But then underneath, you can start to plot the results, but you can only plot the results one building class at a time. And this can be useful for sanity checking the results, and also to help you to perhaps choose an intensity measure type for which to produce your vulnerability models in terms of. One feature of this tool is that you don't need to use the record selection and the upload your capacity curve. If you've already run your response analyses elsewhere, you could actually start from the tool at this point, and you could already upload your records, and it will compute the intensity measure levels for you, and you can upload your response data from elsewhere. So you can actually start from this point using analyses that you've run elsewhere, and it will plot for you the response versus intensity data, and from this point onwards use that data for the vulnerability development. So the next step is the fragility analysis. This is where we're going to apply those thresholds to damage to the response data and calculate the probability of exceeding those thresholds. And also, first we need to do the regression, the linear regression of our cloud data. So we've run our dynamic analysis, we have a cloud of data points, and we now need to apply linear regression. There's 2 choices we can make in the user interface. One is called uncensored regression, and the other is censored regression. Now, uncensored regression will just use all of the data that you've provided, all of the response data, and do a linear regression. In censored regression, we tell the tool not to consider the values that are beyond a given limit. So this is an ultimate threshold multiplied by a censoring factor. So it will take the ultimate damage threshold, the last damage threshold that you've provided, and it will multiply it by a censoring factor. Now, if your ultimate damage threshold is already the point that you don't want to consider the points after, your censoring factor would be 1. but often we do want to consider values that are slightly higher than our last damage threshold that we've provided. So anything above that, let's say that limit, it's the values of those points are not considered in the regression analysis, because as you can imagine, these values here, they would influence this linear regression. They may be points where actually the analysis has not converged because the single degree of freedom structure has collapsed. But we want to take into account the fact that we have exceeded the threshold, that those buildings have collapsed, but we don't want to actually use their values. And that's what's being done with the censored regression. We're taking into account the knowledge that we have exceeded the threshold, but we're not actually using the value to affect our linear regression. So often in your capacity curves, your last point is not fully collapse of the building, it's typically a near collapse point. So we suggest often to use a scaling factor of about 50% higher than that value as your censoring factor. So you need to provide the damage model files. As we said before, you need to tell the tool what is the different thresholds at which different damage states occur. Those thresholds might be in terms of displacement or acceleration, depending on what type of models you're producing. Typically, you would be using this tool, I think, to produce fragility functions for structures, and you're interested, therefore, in the displacement thresholds. So you simply provide for each damage state the threshold in terms of, in this case, displacement. And then, as we said before, the probability of exceeding those levels of threshold will be calculated from the regression. Another option here is if a single capacity curve has been input by the user for a whole building class, you can ask the tool to implement additional building-to-building variability when deriving the fragility function. And to account for that material property and geometrical property variation. And from past studies we've done, we've seen that a value of about 0.3 represents quite well that building-to-building variability. The next module, the final module in terms of developing the models, is the vulnerability module. So there's two ways that we can compute our vulnerability models at this point. We can convert the response data, the EDP data, into loss, where we provide an EDP to loss model, an example shown here on the left. So our EDP here is spectral displacement, and at different levels of spectral displacement, we would provide a mean loss ratio. Instead, if we want to convert from the fragility functions, we use a damage to loss model, where for each damage state that we've provided, we have our loss ratios. So the user must upload this conversion model as a CSV file. We need to have the same number of loss ratios as damage states. And if we're providing a damage to loss model, we just need a column of loss ratios for all with enough values that match the number of damage states. If instead we're providing an EDP to loss model, then we need two columns, one with the EDP value and the second with the mean loss ratio. Now, if I go back to the tool, you see here there's a choice to propagate uncertainty. We can propagate uncertainty. What this means is the tool is using a formula that's been proposed by Vita, by Silva, 2019, which is a formula for the uncertainty. As I showed you in that first slide, that uncertainty in the mean loss ratio. It computes the standard deviation as a function of the mean loss ratio. And this is with a beta distribution. And so if you choose this uncertainty, these values will be computed and output. So finally, moving on to the last two modules, where we are now validating, comparing, verifying our results. So we can run comparisons with the models that we've computed. We could upload our own fragility or vulnerability models that we've computed, or maybe we found in the literature, and we can make a comparison one building class at a time between the function that we've just computed with a tool with another uploaded values. So here we would choose the computed function, here we choose the one to compare, and we can plot the comparison. In the Vulnerability Modelers Toolkit repository, there's a folder called Validations, and this contains the full set of GEM fragility and vulnerability models, according to the publication Martinez and Silva 2020. And so the user could also go and pick up those models for comparison. Though one thing that should be considered is that these models will be in terms of different intensity measure types. Some use spectral acceleration, some use at different periods, some use PGA. So there is a plotting feature at the bottom where you can first plot the GEM fragility or vulnerability functions to see what the intensity measure type is before you make your comparisons. And finally, verification. So this is where you can get to use your models to calculate some risk metrics to see if they make sense, to compare different building classes in terms of risk metrics, because perhaps you're looking at a number of different building classes where you've decided to use different intensity measure types. And so it's very difficult to compare the models just in terms of their vulnerability. But if we now convert them into a risk metric, we can compare them with those risk metrics. So we can calculate average annual loss with the tool. So if we upload the vulnerability function that we've calculated, then we also need to upload a hazard curve. This is a simple CSV file, 2 columns, intensity measure level, and probability of exceedance. We need to provide the investigation time of that hazard curve. Is it the annual probability of exceedance? Is it the probability of exceedance in 50 years, for example? And then I'm not going to go through the theory, but it is convolving that hazard curve with that either fragility or vulnerability function to calculate the average annual. In the case of a vulnerability function, it would be calculating the average annual loss. If you have instead uploaded your fragility functions, it will pick up the last damage state that you have calculated. Now, that is often a near collapse or a collapse limit state. So it would be providing the average annual probability of exceeding that final damage state. If you have computed many building classes, you could upload a folder with all of the vulnerability models, and you can use this feature here at the bottom of the page to plot the average annual losses for all of those vulnerability classes in one go. So whereas at the top here, I'm uploading here a single file, the hazard curve, the investigation time, computing the average annual loss, and it will give me the value here. In this box, I can upload a number of curves, plot the average annual losses, and there I can start to compare my different building classes in terms of their average annual loss. So that's the end of the explanation of the graphical user interface and the 7 different modules. Before we move on to showing you an application, I just wanted to spend a few minutes to talk about installing it on Mac and Windows. You obviously won't be doing this like real time with us, but with the fact that we're recording this, you can come back and look at this at another time, perhaps when you try and install the tool, and hopefully these instructions will be useful. So the first thing to note is that you need Python 3.8 or higher in order to install on both Mac and Windows. And we've noticed when installing on Windows, sometimes users can run into difficulties. So we have here a couple of sort of known issues. One is that you may need to edit your environment variables, adding a path specifically to where the Python executable is located after you've installed it from the Python website. Typically, it's found here within your app data, local programs, Python, but this will depend on your system. So if you're running into trouble, even just using Python on Windows, it could be that you need to edit your environment variables. Another issue we've had when trying to run the tools is that the computer is missing some of these Microsoft Visual C++ runtime libraries. Here's the link. You can also Google that. I'm sure you'd find them. And you need to make sure that you've installed these in order to get the graphical user interface to run. One thing we do recommend, and that a lot of us use, is to first install Anaconda. onto both Mac or Windows. So following the installation of Anaconda, what you can do from either the command line or from terminal on a Mac is to create a virtual environment. So just with this instruction here, conda create -n, give it a name. We can give it any name. In this example, I've called it the Vulnerability Modelers Toolkit. Tell it to install that virtual environment with Python 3.8 at least, Anaconda. So with this command, it will set up a virtual environment for you with Python 3.8 already installed. You activate that virtual environment, and then you can move on to installing the toolkit. So this is what way that we often recommend to do it for those that are not so familiar with Python. So once you have Python 3.8 installed on your Mac or your Windows, now we need to download and install the toolkit itself. I believe in the chat you should have had the links to these, to where the GitHub repository is. But if not, just search GEM Science Tools on GitHub and you should find the Vulnerability Modelers Toolkit. Once you arrive at the web page, this is what you will see. And you need to click on the code button here and then download zip. And you will download the whole of the Vulnerability Modelers Toolkit. Make sure you're on the master branch here. Once you've installed it locally on your computer, then you need to open up. If you're working on Mac, you'll be opening up a terminal. If you're on Windows, maybe it's the command line prompt, cmd.exe. And so you need to navigate to the folder where you have downloaded that Vulnerability Modelers Toolkit and unzipped it. This should probably say where you have downloaded the Vulnerability Modelers Toolkit. So here, for example, you can see I've activated the virtual environment and then I'm CDing to the folder on my computer, documents. It's inside a folder where I have all my GitHub repositories, and I'm going inside the Vulnerability Modelers Toolkit folder. From there, you just need to type pip install -r requirements.txt. So there is a requirements.txt file in this location, and this will give the instructions to install all of the different requirements that are needed by the Modelers Toolkit. So once you press enter, you'll have to wait and you'll see all of the requirements being installed. And you have to wait until that's complete. It may take some time. Once it's completed, you'll then need to enter the GUI folder, so CD GUI folder. And from there, you just type Python start_GUI.py. And this will launch and open up the graphical user interface. Might take a couple of seconds to come up, but just wait and it will open up the graphical user interface. And from that point, you're ready to run through the different steps that I've just presented. If you do want to have a go of running the tool before you have your own input files, there are a number of demonstration files that have been provided on the GitHub repository. So these are all inside a folder called demonstration files. So there's capacity curves there, there's records there, there's a hazard curve. So you can run all of the functionalities of the tool and test it out before you start to use your own inputs. If you're having problems, if you have problems installing the toolkit or running the toolkit, or if you have questions on some of the assumptions, the scientific assumptions, then you can either email the EFEHR risk team, where we're very happy to help answer those questions. So here's the email, or you could join the OpenQuake users mailing list that GEM has. So it's a Google group. And just write your questions there, clarifying that they are about the Vulnerability Modelers Toolkit rather than OpenQuake. And members from GEM, such as Luis and his colleagues, will answer any of your questions. So I'm going to stop my slides there, stop sharing. I don't know if there's been any questions at this point. I can see there's one Q&A. So I don't know if it's been answered, Luis, but I can see there's a question about how does the toolkit find the time histories that are compatible with the conditional spectra for each IM level? It searches the European. So I'm going to let Luis maybe type a response to that if you can see it. If not, I'll do it myself. And I think it's time now because we're running a little bit later than initially envisaged. I think I would move on now to Martina and ask her if she could share her screen. And she will be showing an example application of the toolkit. And we're not going to run the toolkit live because things can always go wrong when you try and run a live demonstration. But she has a video that a screen video that she's already done of the toolkit, which she'll be talking over and pausing where necessary. So let's see. Perfect. We see your slides. Thanks, Martina.
Okay, thank you, Helen. Good morning, everyone. So today, as Helen has anticipated, I will be showing an application of the VMTK that I did for my research using the graphical user interface. So I will start just by very briefly introducing the building we were studying, which is a reinforced concrete infill building located in northern Italy in a site which is characterized by soil type C and topographic class T1. The study was made by some people from the research group of Pavia, including myself, and some people from the research group of the University of Bergamo. So here we have the structural model we had of this building, as you see here. It was made using the software EFEHR-GEM, so it was a 3D nonlinear model. And here you can see the capacity curve, including the bilinearization of that curve. You can also see I have highlighted 4 points, which corresponds to different damage states. We were indeed interested in calculating fragility functions for different damage states, which were coincident with those taken from the Italian building code. So starting from the operational limit state, the damage limitation limit state, life safety, and collapse limit state. So starting from this building, since we only carried out nonlinear static analysis, we were anyway interested in calculating fragility curves and vulnerability one, and estimate some risk metrics. We used the vulnerability modeler toolkit to do so. So I will move to the next slide, where I have summarized some of the assumptions we did, and that you will see during the screen recording I will show you later. First of all, the intensity measure we have used is the spectral acceleration at the fundamental period of our structure, which was equal to 0.5 seconds. The target intensity measure beams we have selected do range from 0.05 to 1.5 G. And for each beam, we have decided to select 20 ground motion records, limiting the scaling of such records between 0.5 and 2. As I have already said, our capacity curve was in the form of a bilinear curve. For the damage model, we have used the one proposed by Martins and Silva in 2020 that Helen already shown. And so we have used it to identify the 4 damage states I have presented before, but we will see it later on as well. And then the damage to loss model we have used is that one shown here to have a conversion from damage state to losses. I will immediately move to the screen recording. So I did this is how we have applied the toolkit to our building. I will go slowly through all the process. Before I start the video, you see here I have indicated the folder where I have installed the VMTK. To run the graphical user interface, I placed this folder here. So I will start the video now. So you will see that I will start the graphic interface by typing Python start GUI.py, and in a few seconds you will see the graphical interface opening. So I will go through all of the steps, starting from the demand. I will stop here now just to have a few seconds more. So starting from the demand module, the first step is to look for the folder where ground motion records are located. In this case, as you can see here, I will navigate in an example folder I had in my laptop, and I have selected the European strong motion database because this was the one I used, but potentially you could also have other databases of ground motion recordings that you may want to use. So I'm selecting it, and I'm selecting as an intensity measure the spectral acceleration at 0.5 seconds, as I told you before. So here, as you can see, you have several options to do the record selection. We selected records based on a range of intensity measure beams. So I have selected the second option and included here the range I was showing you before. So from 0.05 G up to 1.5 G. You can see that there are 6 beams. So the first one, for instance, between 0.05 and 0.1, and then all the others up to the last one, which is 1.5 plus. I have selected 20 records per, I've indicated 20 records per beam to be selected, and I'm also indicating here the range of scaling factors between 0.5 and 2. Now I have to indicate here a folder where I want my selected records to be placed. So you can see here I am creating a folder, an output folder where those records will be placed. So here you see I'm looking for this folder over here. And then I can start the selection of records, which may, of course, take a while because they are a lot of 6 times 20 records. So the tool is looking for compatible records. And as you can see here, while we're waiting, of course, now we will see the plot of the ground motions that are selected, that will be selected, which will be compatible with this criteria we have selected to matching intensity measure beams. Alternatively, we could also select records based on conditional spectrum method. So in that case, we would condition our intensity measure to specific target IM levels. So in the case I'm talking about, we are doing a cloud analysis. In that case, we are closer to a multiple stripe analysis. So I will skip a little bit, going to the part where the selection is completed. Here I will check if the records are there, and as you can see, they are 106, because the tool possibly couldn't find the total number of records I have indicated, because maybe it was too large for the database of records we had. So now I can input some ranges of periods for which I want the plot of records. So I'm looking around 0.4 and 0.6 seconds, including 100 steps. And now we will see the plot of the records we have selected. So we can move now to the capacity tab, where in our case, I will only need to input one capacity curve that I have saved in this folder, hold it as an example. And you can see here, as Helen was saying before, I have two columns, the first one with the spectral displacement and the second one with the spectral acceleration in a CSV format. So this is the file I'm going to input here. So I will select it. I have only one building class because I'm only looking at one building specifically. So I will select just one capacity curve here. So here you can see that I cannot indicate the building class. Here, this is a known issue. So what you can do for now is to skip to the other option and then come back to the one you were interested in. And with this method, you could now, the example building class is visible. So by indicating the, here we can finally see the capacity curve. Moving to the structural, sorry, I will go a little bit. Okay, to the structural module, I need to define a damping ratio. So I will input also here a file where it is indicated, and you will see it here. This is the name of my building class. So based on that, the tool will get the damping ratio from here. Okay, and then so I will select it from the correct file here. Moving forward, I can choose the degradation, if I want an energy degradation to be considered or not. And then I will select the output directory. I have already created some folders. The structural analysis one will include the results of this part of the analysis. By confirming the building class, I will put start here. And so the nonlinear dynamic analysis on the single degree of freedom system are now running. You can see here that you could also start the process. Okay, the nonlinear time history analysis are completed, so we can move to this part over here. We could also start applying the tool from this step if we already have EDPs from our analysis, all the results from our analysis, we can also start by using this this one. Instead, we will load EDPs from the files which were created through the structural analysis we have just run. So we will look for the output folder where those should be saved. So the structural analysis one. And then we select the EDP as maximum displacement, for instance, and our IM of interest. Now you will see that the plot is not showing, and this may be related to some kind of error you may have. In this case, you can check the terminal and see and have indication on what the error may be. So you can see here that it seems that in the structural analysis, there is no file of this type, which is the file with the IM. And we will now understand immediately why. So maybe this structural analysis folder was not the correct one to be selected. So I will go again to the output folder, and I will see that in the structural analysis, the tool has created an example folder where the EDP and IM files are saved. So I will choose this one, and now I'm getting the plot, which I can also see in log scale. Now we can move to the fragility tab. So where we can choose a regression method, we have used the MLE censored one and choose a censoring factor of 1.5. And since we are dealing with a single building, we have also included a building-to-building sigma of 0.3. Now we need to select the damage model file, which I have over here. You can see that this is where the spectral displacement at the different damage states of interest are indicated. You see they are 4 as per each of the damage state we were interested in, with the last one being the ultimate spectral displacement. Again, in a CSV file. So I will select this file as the damage model CSV from here. Okay. Now we can, again, we need to select the EDPs folder, which is, again, the one inside the structural analysis output folder, and then select the EDP of interest, in our case, maximum displacement, and then look for the IM file, which is this one specifically within the structural output. Finally, we need to select the output directory of the fragility functions as well. So I have created another folder called fragility analysis, where all the results will be placed after fragility are calculated. You see they are already created, so we can now look at the plot. And we will have the 4 fragility functions for each damage states. And now I will go in the fragility output folder to see how the results are saved. You can see we have 3 files, 2 CSV files. The first one is the example fragility assay, where all the entire fragility functions are shown, and we will see that. The second one only includes the relevant parameters, the log mean and standard deviation of the fragility functions which were calculated. And lastly, we have also an XML file with the fragility functions, which is the format compatible with OpenQuake. So I will open all of them. So here you have the SA at 0.5 seconds, and then all the fragility functions for each damage state. The second file, as I told you, is collect the log mean and the log standard deviation of each of them. And finally, the XML summarizes the results as you're seeing here. So let's move again to the tool. So now that we have the fragility functions, we can move to the vulnerability function, and we can choose here the conversion type we want to use. We were using the damage to loss conversion, as I already mentioned. So now I will look for the file where this the conversion model is saved, and it's the one I call damage to loss. And here you will see the loss ratios corresponding to each of the damage states we were interested in, again in CSV format. So I will select this specific file as a conversion model. Then we don't need IMs and EDPs since we are looking to a damage to loss conversion type. And then finally, I'm selecting the fragility, the folder where the fragility output are. And select also where I want the vulnerability output to be placed. I have indeed created another folder called vulnerability analysis where I will see all the results. Okay, here we can plot the vulnerability function finally for our building. Let's move to the, okay, now I will show you the output of the vulnerability analysis, which you can see here. Again, you have two files, one CSV, one XML, and we will look at them. In the CSV, I have the spectral acceleration and the loss ratio, and then here I have the XML file of the same function. So now in the compare results tab, we can compare the functions we have just calculated with those included in the GEM library. You can decide to compare either fragility or vulnerability function. In this example, we will compare fragility functions, and I will look here at the library by looking for the fragility function of a reinforced concrete infill frame of 4 floors with low ductility, as you can see here. And then once you have indicated both functions, okay, here you can see that the library is all over here, and potentially you could plot each of those functions to have a look at them each. And here making sure that the IM used in the fragility function of the GEM library was at least comparable to that of my case study. It is not identical, but at least for the comparison, we could do it. So here is the plot. You can maybe see that our building was very fragile if compared to the fragility included in the GEM library. But okay, this is just for an example to show you the potential of this tool to also compare your computed fragility or vulnerability function with those included in the GEM library. Finally, we can move to the Verify Results tab, where we can compute some risk metric. In this case, I will compute the average annual loss ratio. So I will put as an input the vulnerability curve. And then I will select as well the hazard curve of the site of interest, which is Brescia, for the specific IM I was looking for, with a hazard investigation time of 1 year. So now I finally can compute the average annual loss ratio, which in our case was equal to around 0.05%. I have not continued here because we had only one capacity curve and one building type, but again, here you could also plot different average annual losses to compare multiple models. I'm at the end of this presentation. If you have questions or doubts, of course, will be happy to answer.
Thanks, Martina. Thank you. So we have been answering a few questions while you were presenting in the Q&A box, and there was one also in the chat, which has been answered too. If anyone has any specific questions that they do want to turn on their microphone and ask them specifically, we can do that now because we have time. We have one question which has just come in the Q&A box, which is, are there available resources for damage to loss conversion models specifically defined for individual building classes? So there are damage to loss conversion models in the literature. There's obviously the HAZUS models. There's models which have been collected in Italy from past damage data. I don't know if Vito or Luis, who have obviously looked at this for many different areas of the world, want to add something about specific individual building classes. I don't know about getting down to the level of individual building class.
Maybe not necessarily individual, but there are other damage loss models, for example, by Andreas Kapus for Greece. There's also by Xanbol for Turkey. There's also, obviously, Helen, you already mentioned the ones for the United States, and there's the ones from Goretti for Italy that I think you were mentioning. So I'm not entirely sure if damage loss models have been developed for specific building classes, but they have been developed for specific countries, and sometimes even take into account, for example, the rules of the country. Like, for example, in Turkey, that if a building has extensive damage, it has to be demolished. In my presentation, I will talk a little bit about component-based damage loss functions. So I think that will take us a little bit towards more building-specific type of vulnerability, because obviously, depending on the building and the occupancy of the building, we're going to have different components, so there will be different damage loss functions.
Thank you.
I can also add something. Like in our paper from 2016, I think, in we actually end up with a damage to loss model based on component damage. The one that we have in structural and engineering dynamics instruction, the Chopra paper, journal, and you can also find a collection of damage loss models there that we used for references.
Thanks, Louis. So there's another question on, and also Catalina provided a link to the GEMS vulnerability vulnerability database where some of these models are stored. Thanks, Catalina. So can I perform verification validation on damage loss ratio models that I have already performed on an older version of OpenQuake? So I'm not sure exactly what you mean by this question. I think you're asking about, because I'm not sure what you mean. So you've run some analyses maybe with OpenQuake and you want to verify the outputs. So that's not really what this tool is for. So this tool is for developing the vulnerability model. If you're interested in validating and verifying losses coming from your models, so that's a different sort of need, then perhaps in the future there'll be another webinar on GEM's database that they're currently putting together, which is a database of scenarios, of past scenarios, which would allow you to run your models with past scenario earthquakes, where they are collecting all of the input that you need in terms of the rupture model, ground motion models, some recordings of those past events, and also all of the observed damage and losses. So I don't know the official name of that tool, Vita, but I imagine in the future that will be something that we can have maybe another webinar on in the future.
Yeah, on the validation of risk models, I think it's something that is very necessary. I think if we see, I think 95%, if not more, of the vulnerability studies that you can find on the literature, quite often they don't go to these two tabs that Helen is showing now on the screen. You know, there's very little comparison with other results, and there's very little verification of the results. So it has been the case that at GEM, we do collect vulnerability functions from the literature, and we do want to use them. But once we estimate some of these metrics that Martina was mentioning, you know, average annual losses or losses for specific return periods, the results are not that realistic, and often because some of these functions are being used for the first time in scenarios or probabilistic risk assessment. So I do think that you know, probably a webinar about validation and verification of risk models in the same way that EFEHR already organized one with a stronger focus on the seismic hazard. I think that's a very good idea.
So I hope, Vivek, that we answered your question correctly. If not, let us know. I don't see any more questions right now coming up on the Q&A. As I say, if there is any more, just add them later as we carry on through the webinar. I think we are sort of running ahead of time, so I think we would take maybe a 10-minute break. If you would like to go to the website, maybe we'll put the links, maybe Martina, she can put the links again in case you joined late. We can put the links to the Vulnerability Modelers Toolkit. And if you want to go, if you have Python, for example, already installed on your computer, and you want to go and try and download it and install it during this 10-minute break, and then if you come back and you have questions for us, we could do that. And that's not exactly what we were planning in this session. We weren't necessarily planning to run through installation with you and live running. But if you do try it out in these next 10-15 minutes and you have questions and issues, you can ask us while you have us here. So let's just do a 10-minute break until 11:30, and then we'll come back with Luis, who will be giving a much more detailed view of the, let's say, the background code, source code behind the tool, so that you could make some changes and not necessarily use the default assumptions that we've been presenting to you up until now. So see you in 11:30. Thanks. So as I've mentioned before, now we're going to move into the more advanced user part of the session. Luis Martins, who is the main author of the whole Vulnerability Modelers Toolkit, will be giving us a tour of the actual source code itself and talking about some things you might want to do if you want to get your hands on the source code. Luis, over to you. Thanks.
Thank you, Helen. I'll share my screen now. Hopefully you all can see my screen.
Yeah, looks good.
Okay, fantastic. So I've divided this intervention into halves. The first, we'll just go through the repository, and hopefully you had time during the break to navigate to this web page, but if you haven't, this is where you land when you go to the repository, to the GitHub repository where the toolkit is hosted. This repository is basically divided in modules similar to the graphical user interface, but they have some extras that I recommend you to have a look. For example, the readmes are very useful. You'll have their information on where the data came from and how it has been implemented. For example, here in the validations, you can see that the functions have been collected from this publication. But the main structure of the repository is very similar to the graphical user interface and is separated in folders. Starting with, for example, capacity, you'll see here a collection of either functions that are actually used on the vulnerability models toolkit or something that will be very useful for you in the case of you wanting to use the Python scripting capabilities. I'll go through a couple of these in the presentation in a short while, but let me just highlight a couple of things here. Something that you don't see on the graphical user interface, but it's here, is, for example, this analysis, which hosts basically the OpenSea's model, the single degree of freedom system, and all the implementation. You'll see as well all the functions that are either used or it will be very useful for you when you want to do the regressions in this fragility vulnerability folder. And the way you use it, you use this tool is from this set of a lot of functions. You can basically call them in your script and use them as they are, or you can edit them as you feel fit. You'll find this folder here, demonstration files, like Helen said previously, some examples so you can double check your inputs to see if the format is okay. I also implemented here a full-on example on how to run the toolkit using Python. But that said, let's go and have a quick dive into the actual workflow and some aspects that you may feel interested to apply in your own use case. And with that, I'll start my presentation. So the first situation that you may find yourself is you probably noticed baseline for all of this is that the vulnerability models toolkit needs a capacity curve. Here at GEM, basically you get our capacity curves through mechanic models, through mechanics. So we get displacement, yield displacements, ultimate displacements, the period of vibration, and you build your backbone curve. But you may find yourself in a situation very similar to Martina, and is like, okay, I have built my own very detailed numerical model. Can I still use this tool to go and develop vulnerability, fragility, and vulnerability functions? And I'll go with this example. This is actually a building that I analyzed some time ago. It's an irregular building, 7 stories, built in Colombia, and this is a 3D model, so it's a very complex model. And bear in mind, you could have made this in any of the software packages that you are used to, say OpenSea, SAP, or whatever you feel more comfortable. And so I built my model, but I know that's like performing single degree of freedom performing a nonlinear mystery analysis on this very complex 3D model can be quite challenging. So similar to what Martina has done, I can make a pushover analysis and get my capacity curve. Here, we are faced with a problem. So my capacity curve, because I did numerically, it's a lot of points. But the VMTK requires you to input something that's compatible with the pinching for material from open seeds, meaning you need to linearize your capacity curve. And here is the first good to have function, for example, in the VMTK. This function here that it's hosted in the capacity_start.py file uses an interpolation, a depth bit interpolation algorithm to basically linearize any shape curve. And here you have an example. And as you can see, now I can convert these to spectrum, to the acceleration, displacement, response spectrum format, and proceed with my workflow and the vulnerability models toolkit as they are. Or let's imagine that indeed I actually managed to run nonlinear mystery analysis on my 3D model, and I didn't want to use the simplified capacity curve and convert it to a simplified single Fourier freedom system. And I collected my response. For example, here you have the actual response of the building in 2 directions. And here, for example, if you want, this is this is actually a function that's used on the vulnerability models toolkit with a sensor regression. Here is, I'm highlighting here the actual path where you'll find this function. But that said, it's like here you can implement your own analysis algorithm if you want. You don't need to be cloud analysis. If you want, you can do perfectly fine multiple stripes. That's the advantages of the scripting capabilities of Python. So once you have your response and you run that function, you can come up with your fragility. Now I want to go one step forward and move towards vulnerability. Here's another function that's actually used in the toolkit, and a nice to have function as well, handy. Again, in the exact same page, you'll find this calculate vulnerability curve from damage to loss. And below, you'll also find EVP to loss. And this will provide you with your vulnerability functions. Now, can I use other ground motion selection techniques? Yes, you can. And you'll be adding your methodology here in this daemon folder in the select ground motion records. So if you want, for example, to have a selection and scaling that applies to multiple stripes, where you have the same set of records, a set of records for each intensity scaled to match that intensity. You'll be adding this here. Now, those who are familiar with OpenSeeds and want to experiment with other types of structural modeling, you can edit and change some of the modeling assumptions that we have in the tool. For example, we have implemented pinching for with the degradation parameters from Dimitri Zombatsic. If you navigate to his webpage, which is linked below, you'll find that he has a script called simple sdof.tickle. And basically what we did was transpose that to Python, and we applying it. But OpenCIS offers you a myriad of other ways of modeling hysteretic behavior. Here are two examples. You can find a lot more in the documentation. And what you'll be doing would be to go to this script, adding a new script if you want. You'll be editing these lines here. These are the lines that take the points from the capacity, converts them to force displacement, adds the degradation and parameters to the pinching for, and builds the pinching for material. Another thing that you may want to edit, damping. Our general assumption is that damping is mass proportional and is introduced with a Rayleigh command. Imagine that you want to experiment with stiffness proportional, or a combination of mass and stiffness proportional, or other kinds of damping, if you will. Basically, you'll be entering here and you'll be editing this little bit of code. Here, basically, what I'm getting is the frequency of vibration, computing with the damping, and then the alpha M is just the parameter for the Rayleigh. The good thing about using Python with the vulnerability model toolkit is, especially in the case of portfolio analysis, you can capitalize on the ability to parallelize processes. And I use this basically every single day because we work at the global scale. We have multiple over 1,000 building classes on our database, and I cannot go one by one. So what this is really useful is, like, imagine that you have an exposure model and you want to build the risk, calculate the risk for your exposure. You can extract your unique building classes that you find in your exposure model. It could be manageable if it's a very small exposure model, say a city, and maybe you have half a dozen building classes. Maybe you could do it on the graphical user interface one by one. Or in the case, for example, of Europe, where the risk has a couple of hundreds of building classes. So what the good thing you can do is, like, send multiple runs to each thread, and you'll get basically all your results at the same time in each thread independently, and then you just have blocks of functions already calculated. This is actually relatively easy to implement on Python. Here's a very generic example using the multi-processing library, where basically what you do is, like, you create a function that you want to parallelize. This function will contain the portion of the workflow in the vulnerability model toolkit you want to parallelize using all the functions. And then basically you create a pool and you send that function to as many threads as you can. This is, again, very useful for portfolio analysis. where can I find examples of this in the vulnerability model toolkit? Like I alluded before, there's actually an example file that you can go through, and I made it actually not parallelized. So I gave priority to intelligibility, and so everything is like very clear, so you can follow along. And later, if you want, you can edit this and make it parallelized. But if you're starting now, this could be a good point to start. Plus, a request before we go to Q&A. You can use the issues feature in the GitHub in case you find any bug in the vulnerabilities model toolkit and you want to help us improve the code. You can report there. We actually want to start a community of with this tool, so there is a discussion chat that you can ask and engage in conversations. Some of you already did that, but so far it has not been a very successful implementation. I hope this changes today. You can engage with other people in the community. You can engage with us here as well. Last but not least, I really hope that you help us improve the toolkit and add functionality to it. And for that, you can, for example, fork it. And this allows you to experiment with the code and do all kinds of changes that you want. And then submit your changes to be reviewed by us. And later, if they are deemed good, they'll be added to the master branch. And with that, I close here. And if there's any question, I'll be more than happy to answer.
Thank you, Luis. Thanks. I don't see any questions in the Q&A right now or on the chat.
Come on,
so so I don't know if Vito, if you have anything you want to add on what Luis has presented, or anything that was additional comments. Otherwise, I guess we'll move on to your presentation. But do you want to say anything specifically about the GitHub and the?
Maybe I will, during the presentation. Yeah, I will just encourage, obviously people to provide code. Obviously, the other example that we have in terms of, I want to say, very successful open project is this tool that GEM supports called OpenQuake, and it has a lot of features there that were proposed by others, like, for example, from ground motion models, from different ways of doing losses using shake maps. So I think that has been quite successful. So it would be, amazing if this tool also becomes a little bit like OpenQuake with contributions from different people from the community.
Definitely. And if people don't know how to code in Python and not capable of doing that, then please use the discussion tab, as Luis was saying, for suggested features, requests, and we've seen some today, even on the Q&A. And I think this will come up in Vita's presentation of additional features and directions that this toolkit can take in the future. So I guess let's move on to Vita's final presentation. There is one question's come up. I don't know. The question is, Luis, in order to use the functions that linearizes the capacity curves, we need to install or import the entire toolkit, or can it be used independently? I think that's a good question generally about using these functions.
You can literally just, if you just want one function, you can literally just go to the repository, copy and paste the function in your IDE of choice and use it, as long as you have all the dependencies that it requires. So that's fine. And
But probably the entire tool is not that big, right, Luis? So I would
No,
really
no.
recommend, people to install the whole thing, because this way, at least every time that I have to install a new tool, if it depends on libraries, sometimes it's a nightmare because you install the libraries, there's different versions of the libraries. So
Yes, most definitely.
yeah, usually by installing the whole thing, at least you know that in theory, everything should be compatible.
That's correct. Yeah, it's like definitely let's say the recommended way, get the entire tool, and if anything, because probably later in that day that you thought it just one function, you'll probably find a use for yet another function, so you'll need to go again. If nothing, you'll get that in one go.
So some of you might be familiar with GitHub, GitLab, and you know that the best thing probably to do is to clone the repository, because in that case, you can continually stay up to date with the latest developments on the code. If you're not that familiar with using Git, you can simply just download a zip file, install it, or unzip it on your computer. But just make sure maybe to go back frequently to the website to see if there has been updates since the last time that you downloaded it. There's another question actually come up. Does the Vulnerability Modelers Toolkit have the possibility of disaggregating the hazard for Europe for the purposes of generating the conditional mean spectrum? No,
it does not.
It does not.
OpenQuake does that.
It leverages on OpenQuake, actually.
Exactly. So you're asking here also about the European hazard. I think Laurencio unfortunately has left us. He has another meeting that he had to go to. But I think one thing that's not yet been released from the European seismic hazard model is the disaggregation. But I know that there are plans to release it. So they are running disaggregation of the European model across many sites in Europe. So once that's done, you should be able to go to the hazard.efehr.org platform to get the disaggregation results of the European hazard model, which will be in the OpenQuake format because the OpenQuake engine has been used for the hazard, and then you'll be able to upload them to this toolkit because it's the same format. Yeah. Okay.
Yeah, and maybe just before I start, Helen, I think you mentioned this and Luis as well, but just to emphasize that, one of the beauties of using these tools is the ecosystem of file formats and data and tools. A lot of the things that go into the Vulnerability Models Toolkit, it's either simple CSV files, but for example, for the disaggregation of hazard, it basically digests directly the output from OpenQuake. So you do need a PSHA model. You run your analysis, you have your seismic hazard disaggregation, and then you don't have to, to waste time like I've done many times in the past, post-processing files, like everything is already compatible. And then of course, at the end of your calculations, because it also exports, this XML files, which is already in the OpenQuake format, I think it also facilitates then running risk analysis or earthquake scenarios. So this was definitely something that we were aiming for while developing these tools.
And sorry, Victor, maybe you just said this and I was thinking of something. I was thinking while you were talking, maybe I'm going to repeat what you've just said, but a new feature that Luis put in recently is the output of this toolkit is the XML files, which are then the vulnerability and fragility XML files that the OpenQuake engine uses. Did you just say that, Victor?
I did. Yes.
Sorry. Okay, perfect. I should have listened to you rather than thinking. Okay. So,
yeah, it was a deja vu. No, it's good. It's good. It's
very clear
to
now.
emphasize. Yeah.
Thank you. Okay. Let's move on. And if there are any more questions, continue to put them in the Q&A and we'll type your responses. Thanks, Peter.
Yeah. So, the purpose of this presentation is just that, vulnerability is such a complex world. It's something that it's, I would say, more comprehensive and more mature than, for example, even risk analysis. Vulnerability has been done, at least for 4 decades, maybe starting a little bit with capacity curves and the empirical methodologies that Helen was mentioning previously. So the methodologies that you will find in the Vulnerability Models Toolkit is one of the many approaches that you can follow. We're quite aware of that, and there's different advantages and disadvantages on this methodology. So the purpose of this presentation is just to show basically what we're doing now at GEM, or focusing a little bit more at GEM, and how in the next 6 to 12 months things will evolve, and they will evolve quite rapidly. So a lot of the functions that we've been using at GEM, as Luis described, and Helen also initially, it starts with the capacity model. And this is obviously very simple capacity curve, but it could be something a little bit more complex, like Luis mentioned on the bilinearization of the curves. It could be something with 4 branches, for example. It is possible for you or not to propagate the uncertainty on the capacity. For example, if you know probability models to sample the yielding and the ultimate displacement, and if you know also the correlation that exists between these 2 metrics, but it basically you can produce one or many capacity curves. You run your nonlinear time is to analysis, and you can have fragility or vulnerability curves. We also understand that basically it's quite important for specific parts of the world and also for specific purposes, like, for example, the insurance industry, to have losses for the building and then also have losses for the contents. And this is something that we're doing already. You can have functions for the building, so the structural and non-structural components, some of them drift sensitive, some of them acceleration sensitive. And we can also have functions for the contents. We can run everything separately in this tool that we were mentioning in OpenQuake, and then we can sum or aggregate the losses at the end. And it's also possible for you to calculate the weighted vulnerability function if you do not want to run the calculation separately. So why are single degree of freedom system oscillators useful? So this is actually a question that we get all the time when we talk about risk assessment within the the GEM framework, or when we talk with different partners. So some of the reasons is the simplicity of the capacity models. It is possible for us to use a lot of papers from the literature, because some of the papers focus on the whole thing, like fragility and vulnerability, some papers just on capacity curves, some papers just on periods of vibration, on thresholds for the yielding and ultimate displacement. But because this is a relatively simplified model, for each one of the building classes that we have on the global vulnerability model, and it's more than 1,000 vulnerability classes now, we get the chance to use or to incorporate as much as possible many papers from the literature. I will also say that I think initially single degree freedom systems almost got a bit of a bad reputation because they were obviously quite simple initially. But I think in the last years, there's been like a few formulations to try to incorporate, for example, strength degradation, not use only two branches on the capacity curves on the hysteresis model. And this also helps us to have a more realistic view of the actual behavior of the structure. For some of the building classes, there's no studies, of course. If you think about, slums in some parts of the world, or specific building classes like wattle and doubt, it's not like we have, shaking table tests or even pseudodynamic tests or a lot of numerical analysis for those buildings. But through expert opinion, or even by comparing with other building classes, it is perhaps slightly easier to come up with some capacity parameters for this, let's say, informal or non-engineer building classes. And finally, because these models run very fast, it is possible for us to run different versions of the vulnerability model. Then we run earthquake scenarios, we do probabilistic risk analysis, we check average general losses for different return periods. And then we start understanding, well, for this building class, we have not witnessed this level of losses, or we expect higher losses. So let's go back to the drawing board and understand if the capacity parameters have to be adjusted, or for example, if we need different ground motion records. And this can be done basically through several iterations. So there were some advantages in using single degree freedom oscillators. And with that, we developed this global set of vulnerability functions. I think in 2008, we had maybe close to 600 functions. Now we have much more than 1,000 functions, because of different types of construction, different code regulations, different occupancy types, of course. But we use those sets of vulnerability functions to calculate losses at the global level. This was released in 2018. And there will be a new version of the global seismic hazard, global exposure, and global risk that is going to be released in June this year, on the 13th of June. Also for rapid loss assessment or earthquake scenarios, I'm only including here an example that my colleague Anirudh Rao computed on the day of the tragic event in Turkey and in Syria. But with these functions, because it covers all types of building classes, it was possible to basically quickly estimate losses for specific events. And this is something that as part of this project, European project called Aristotle, we will be doing. And this is very useful because basically we can go back and forward, check the losses, check the vulnerability, and often either create new fragility functions, which can be done relatively quickly, or to calibrate existing ones. I also wanted to mention that yesterday when I was doing this presentation, I went to check, which publications were citing either the vulnerability models toolkit or this global vulnerability set that was developed using some of the functions from the vulnerability models toolkit. And I think one of the beauties of developing these functions in this open source environment and open access environment is that other scientists which have expertise on specific types of analysis will use either part of the functions or part of the vulnerability models toolkit and extend this and apply this to other purposes. I'm only including here some work from other people that I thought was extremely interesting. But obviously, I hope that this list will continue expanding. Something for example, what was quite interesting was to use some of the initial parameters to do, for example, damage-dependent fragility functions. But now let's go to the bad stuff. Why do we need also to move to other methodologies? Why single degree of freedom systems might be insufficient, and why are we going through this phase of trying to expand the vulnerability methodologies? So there are many phenomena that cannot be captured by single degree of freedom systems. I'm only including here some, but for example, higher modes of vibration are not well captured. Obviously also torsional effects and so on. The damage assessment of some components require proper estimation of the peak floor acceleration or velocity or interstory drift as opposed to global drift. This is also something that single degree of freedom systems, they can give you these metrics, but using yet more approximations. And that's what we're trying to avoid. In buildings with an even distribution of values across the floors, it might be necessary to have specific damage functions. There was actually a question on the Q&A that was specific about this, and I will talk a little bit more about this in a second. This is, for example, very important for industrial buildings. You might have industrial buildings, for example, with just 2 stories, but 90% of the value of those buildings, it's on the ground floor because it's all the machinery. And those buildings, we should use PGA, for example, for the ground floor, and then spectral acceleration maybe for the upper floor. But clearly the single degree of freedom systems are not ideal for these cases. We can approximate some of the analysis, but again, that's what we're trying to avoid. And estimations of metrics such as business interruption, disruption time requires detailed information about contents and structural components. So again, using specific EDPs for this aspects is quite important. So obviously we come to this slide many times a year, in fact. So we have single degree of freedom systems, and on the other extreme case, we have 3D models. And we've done, obviously, 3D models, complex modeling for specific projects. But obviously, we understand that at the global scale, more than 1,000 building classes, I hope one day we might get to this situation, but it's definitely not where we are right now. So we obviously have to do a compromise between the computational effort and the level of complexity. I just want to mention that from using many of these 3D models and reviewing many of these 3D models, I will say that having a more complex model does not necessarily mean that your model is more reliable, because then you also open a bunch of other problems related with how you calibrate this numerical models, and how you also collect, the geometric, the mechanical, and the dynamic properties of some of these models. So it's not just, let's say, the computational effort is also lacking a lot of data that is necessary to properly calibrate these models. But we thought that at least as a next step, why not use the stick models or the fishbone models or the stick and mesh models? They have been used. I'm by no means saying that this is, a scientific novelty. They have been used for many years. There are a few publications, even from the World Conference I think in Lisbon in 2012, that were already mentioning these models. But it's still an approximation, but it allows us to do perhaps a slightly better modeling of the different TDPs on the different floors. And this is what we're doing right now. So basically, we have, Louise has worked a lot on this and basically creating tools that can convert the single grid freedom systems into the stick and mesh models. And this is, again, quite important because, as I mentioned previously, we have more than 1,000 building classes in the global seismic risk model, and we need to make sure that everything is still compatible with the current model. Obviously, this conversion requires a lot of knowledge about structural dynamics and mechanics. We have to go back and forward a few times to basically understand how the stiffness and the mass for these models has to be distributed, and how we can also take into account degradation if you run this type of models. But this is just to show you some examples for some of the building classes. You have the initial capacity curve, so basically the one that we obtain if we do a pushover curve with the single grid freedom system. And then on in blue, we have already the capacity curve that was obtained by doing, let's say, the equivalent pushover curve on the stick model, on the multi-degree freedom model. So far, the comparison has been quite good. But now, obviously, we have the advantage that I can run my nonlinear dynamic analysis in my stick model. I can see basically what are the list of IMs that I can extract from my ground motion models, exactly in the same way that Martina explained previously. But now it's possible for me to take different metrics like acceleration, like peak floor acceleration, peak floor velocity, or the maximum interstory drift from the different floors. With this additional information, I can now use damage or cost functions. For example, maybe the most famous or complete source of damage and cost functions based on these EDPs is FEMA P58. And some of these functions can be found, for example, on PACT. But there's been a lot of papers, a lot of research in different parts of the world developing this type of functions. Some of them, for example, using shaking table tests, some experimental results, but even adjusting these functions that were originally proposed in PIMA P58 to other parts of the world. There's a lot of work, for example, for Italy and Mexico and other parts of the world. But with that, basically, I can now have different loss ratios. For example, if we use computer equipment, different loss ratios. So basically, the fraction of equipment that is expected to be damaged or lost on the different floors, and I can have an aggregated loss ratio because, for example, I might have the cost of this component for the building and not necessarily per floor, but it is possible to apply either per floor or at the building level. How is this done? So we can basically, what I'm showing here is just for one ground motion record, right? But now I can use either the vulnerability models toolkit or the vulnerability factor, but I can repeat this for hundreds, if not thousands, of ground motion records. So I'm basically building my plot of log IM versus log EDP. Again, it can be different EDPs. I can use my damage or cost functions, and I can have basically a vulnerability function per floor. Okay, and this is, for example, particularly interesting. Even if I was talking 2 weeks ago with some colleagues from the insurance industry, and sometimes there are specific insurance policies for different businesses, which might be in a specific floor of a building. So this obviously opens already the possibility to have vulnerability functions for contents or non-structural components, which are in specific locations of the building. Or of course, we can calculate a weighted function and have just a single vulnerability function for the building for a specific, let's say, content or specific component. and run my calculations normally. And this function can be weighted, for example, based on the value of the contents on the different floors, if the value differs. So just to move away a little bit from economic losses, and I will talk a lot about also human impact, but also something that we want to do, and because of several projects that GEM has led in the last years, is to expand this framework to also cover disruption time, or for example, business interruption. So a lot of these functions, these cost functions, can also be either converted or they provide already directly disruption time. So we can have different disruption times for the different floors, for example, and then assuming that the repair of the damage on the various floors is done at the same time, we can have a maximum disruption time based on the maximum value across the different floors. We have now a person that is actually collecting all these damage functions from all around the world. Obviously, PACT is as I mentioned previously, it's one of the most important sources of this type of information, but is obviously very tailored to the United States and to the components and the way that this contents exist in the United States and the components are built in the United States. So we are building this database of damage functions, cost functions, and this is also going to be part of the next version of the Vulnerability Models Toolkit. And again, is basically trying to make sure that this collection of damage functions are useful for places like the United States, but also useful, for example, in places like Southeast Asia or in Africa, where obviously the contents and components have different values, but also very different ways of building. Now, everything that I mentioned until now, it's very much focused on damage, structural damage, economic losses, loss ratios, disruption time. But it's also extremely important for us to also think about how can we then expand these different functions into human losses and the human impact. So basically, how can we expand this and to estimate fatalities, injured, population left homeless. And for that, what we're doing is ensuring that we can now convert these functions that are going to be produced by the Vulnerability Models Toolkit, and we want to extend this to the human impact. So one of the main challenges that we have is that a lot of these models, a lot of these functions, basically they do not give us collapse. They give us what we call complete damage. I think this is damage state 4, for example, if you think about European microseismic scale from 98, or the complete damage, the definition by ASUS. It means that the building is damaged beyond the repair. It might collapse, and that's when fatalities start to increase, but maybe it doesn't collapse. But it is important for us to understand of those buildings with complete damage, how many actually collapse. So this jump here, and then from the buildings that actually collapse, from the people that were trapped inside of buildings that collapsed, how many actually died. There are several studies that have tried to address these questions using, for example, detailed 3D analysis. We've done also some of this analysis for unreinforced masonry buildings, but because we have this global set of vulnerability functions, we have a global mosaic of seismic hazard models and global exposure, we're trying to address this problem in two fronts. So again, going through the detailed 3D analysis, but also looking at the global, let's say, panorama and try to understand, can we calibrate collapse rates and fatality rates using losses that were observed, for example, since 1950. I will not spend too much time on how have we brought losses from the past, like 1950 to today. This is part of the work of one of our PhD students, Salvador Ramos, and this will be explained in a publication. But basically, it is possible for us to look at losses since 1950 and estimate what are the average annual human losses. And then what we can do is the following. Let's say that I use the global seismic risk model of GEM, and I estimate average annual losses. And to do that, I have to use a set of vulnerability or fragility functions, like the ones that Luis was mentioning previously. And I have to establish some initial rates, fatality rates, and also collapse rates. And this is done using data from the literature, but also using some damage databases, like the one for Italy or the one for Nepal, the one for Mexico that has a lot of detail. I apply collapse and fatality rates, and I will estimate average annual fatalities. Okay, then I can compare this average annual fatalities with my empirical fatalities in different countries. And I will note that this is not the same. So basically, we need to adjust the fatality rates and the collapse rates for the different building classes. And we run this process many times, many iterations, until basically the fatalities that are coming out of our analytical models match the observations from the past years. There is obviously a lot of limitations with this process, because you could tell me, well, for a lot of the countries, I don't have enough events because simply there hasn't been destructive events in the last years. You could also tell me that this is going to be biased because it depends on the global seismic hazard model, right? If we use different seismic hazard models, we would have different average annualized fatalities. That is all true. But again, as I said, there's different ways of trying to calibrate fatality rates and vulnerability rates within this global vulnerability model. And this is just one of the ways that we are currently exploring. So for the next release of the global vulnerability model, and also for the vulnerability models toolkit, we would like very much to already include economic losses according to these three components. So non-structural components, structural components, and also contents. The toolkit will be able to do already fragility functions for structural damage. This is something that is already included, but we would like very much to be able to provide globally calibrated collapse rates. And then the toolkit will also now export actual collapse fragility functions. We also want to make sure that we use these rates that I was mentioning previously, and the models at the floor level using the stick models and the vulnerability models toolkit will also be able to export disruption time and repair time based on this cost and damage functions. The final thing that I want to mention is that every time that we are developing these functions and using this vulnerability models toolkit, we're quite limited because the vast majority of the fragility models use cumulative log normal functions. I think you've seen probably this equation and this shape of the curves in many times in many papers. I think some of the reasons for this is obviously for mathematical convenience, because if I have my fragility functions defined by a parametric function, then it's very easy for me to do convolution, for example, with seismic hazard curves. And I can code this in 3 or 4 lines in my framework, but we do understand that the progression of damage does not necessarily follow a cumulative log normal function. We do know that if the dispersion on the function is too high, then the tails of the fragility function can lead to unrealistic levels of damage and levels of loss. And we also know that defining the fragility functions is only in terms of one intensity measure, whether it's in PGA, spectroacceleration, or even the average SA, is also quite limitative. We know there's a lot of limitations and a lot of drawbacks from using just a single intensity measure. So something that we've been exploring, and Louise has done a lot of work about this, is what if we try to start using a lot of this new statistical models, a lot of these new algorithms, machine learning algorithms. A lot of them also had some bad reputation in the past because they were a bit of a black box. I think the field has evolved a lot in the last years, and now it is actually possible for you to look at the different models and understand exactly what's going on there and the parameters that are being used. And the truth is that there's now dozens of publications, not necessarily on earthquake engineering, they use some of this model, whether it's neural networks or random forests, and they do lead to better results. So in these cases, I don't have to limit my models just to PGA, spectroacceleration, PGV. I can provide all of this, and including maybe duration, maybe the tectonic region, maybe average SA. There are many intensity measures that I can now provide instead of just using one. And I was mentioning in this slide that I would like very much to be able to produce all these different metrics. So why do I need to have a different model for each one of these metrics and not using a single model that is basically going to give me directly loss ratios or my EDPs, or for example, already disruption times directly. So what do I mean by this? And this is also something that we will be doing. We will generate obviously the different models, the fish bone models or the stick models. We will do the dynamic analysis and export all the IEMs for the different floors. We will train, I put here a neural network, but it might not be a neural network. It could be other algorithms. And we will test whether conventional fragility and vulnerability functions perform better than these neural networks. We have done this, one of my students have compared only for some specific building classes, not for all the building classes that exist in the vulnerability model. And we try to understand whether the vulnerability functions that come out of tools like the vulnerability models toolkit, what we call the Scholar IEMs, are better than neural networks. We use different metrics to try to assess this, but it is very common that we use these two metrics are used, the efficiency and sufficiency. And we can see that at least in terms of sufficiency, the Scholar models quite often are not sufficient, okay? Though I will say that average SA tends to be better than some of the other conventional or more traditional intensity measures. But when we use an artificial neural network, the sufficiency improved significantly, and also the efficiency, you can see that it's much lower, the efficiency, which is what we want, okay? The efficiency is higher because the standard deviation is lower. Petrus also compare for specific earthquake scenarios in the Balkans, and we came to the conclusion that we managed to replicate damage from past events slightly better when we're using this type of models in comparison with Scholar models. So this is my last slide. So just to say that we want to go also a little bit beyond just using the Scholar models, just using log normal functions. And hopefully we'll be able to provide in a single model capacity parameters. So for example, let's say that you don't have a pushover curve, but you do know the period of vibration of your building. You do know, for example, what is expected to be the yielding drift for the different floors, the ultimate drift, for example, the shape factor from the different modes of vibration, and you want to provide all this information into a neural network. Let's say that you have demand parameters, because basically you want to develop fragility functions for a specific part of the world that is characterized by stable continental records or active shallow or subduction or volcanic. So it will be possible for you to specify these parameters, and then the neural network will basically rely on data that was previously input that used this type of parameters. And finally, I just want to say that we also want to make sure that it might be possible for you to export EDPs depending on the location of the building, understanding that, for example, for high-rise buildings, you might have different IEMs as you get to the top of the building, or for industrial buildings, it might be quite important for us to take into account if we're trying to assess damage for the ground floor or the upper floor. So with this, I just want to thank you very much for attending the webinar, and obviously quite happy now to answer questions.
Thank you very much, Vita. Thank you. Just on this last point on the machine learning, is this something that you plan to actually integrate in the vulnerability modelers toolkit in the future, or would that be something that would be feasible for users to run from there, or not necessarily?
Yes, so the idea would be exactly that. And by the way, not just on the vulnerability models toolkit, because I think one of the big challenges of using this type of algorithms, despite the fact that in all fields that have been proved to lead to slightly better results, is that, let's say that I produce right now my neural network. If I want to do now event-based risk analysis, like what do I do? If OpenQuake is not able to digest this type of models, then I have this very good model, I hope very good model, but then I cannot use that. So something that we want to do is also to be able to incorporate this on the vulnerability models toolkit, okay? And then the file that comes out of the vulnerability models toolkit can also be digested by OpenQuake, so then I can use this type of models also in my risk analysis. I think this will be quite important because I spoke with so many people about using this type of models or vulnerability. And this has always been like the big challenge, like, okay, I'll publish this, and then what do I do with that?
Perfect. Thanks for the answer. So we do have a question on the Q&A, and one of the participants has also thank you has answered it, but let's hear your take on it as well. So the question is, a simpler surrogate model which has a capacity curve fitted to the curve of the original more detailed multi-degree of freedom model, will it behave similarly in the time history analysis? So I think this obviously depends on are you looking at low-rise buildings, high-rise buildings with many degrees of freedom and so on? So is this something that you're looking at as well in terms of valid or calibrating your simpler models to make sure that they do have similar response to the multi-degree of freedom? Yeah,
that's the $1 million question, right? If the stick models or the single degree of freedom models could really replicate exactly the behavior of 3D buildings, then why would we have go for the 3D buildings? So we have done some comparisons with Turkish buildings a long time ago, I think maybe 3 or 4 years ago. When we did this analysis, our goal was actually to try to provide correction factors, because we thought, okay, for high-rise buildings, single degree freedom systems are definitely not going to replicate the behavior that well. There were some situations where we did notice some discrepancies, but overall for regular buildings, the comparisons were relatively good. I will say that because of this concern, and also because if we're going to be now using stick models that can export more EDPs, I do think it is our responsibility to also prove that this is giving reliable results. So the student that I mentioned previously, Salvador, is modeling 4 times 2 codes times 2 occupancy times. So is running more or less like 12 buildings, 3D buildings, realistic buildings, and is doing this analysis. So running the 3D models, is using OpenSys to do the 3D models, then obviously grabbing the capacity curve, developing the stick model, and then doing these comparisons. I will also say that there are already also a few studies, it was conference proceedings, if I'm not mistaken, where this comparison was done, and overall, it was the agreement was quite good.
Thanks, Victor. Yeah, I would say if you're using the vulnerability modelers toolkit, especially if you're using it as more of a basic user, maybe you have a 3D model where you've done a pushover analysis and you've turned it into a capacity curve, and you're using that then to produce fragility and vulnerability models. If you can run some dynamic analyses on your 3D model, it would be worth comparing those results with what you're getting from the single degree of freedom system through the vulnerability modelers toolkit, at least in terms of those peak displacements and as a first check. So
yeah, that's right. And by the way, Helen, maybe, let me actually take this opportunity for the people that are attending this seminar, or the people that might hear this video in the future. If you do have already results from 3D buildings and neurodynamic analysis, do share those capacity curves and the response that you have obtained on your past studies, maybe work of past, PhD students. Do share that with us, because I think that would be extremely useful for us to now build a stick model, compare with the results you had in the past, and see if indeed these simplified models can replicate that behavior.
Thanks, Victor. Another question out of curiosity, is the current work at GEM about machine learning for vulnerability modeling based on basic evolutionary machine learning algorithms? I hope you understand that better than me.
I don't know, so I can tell you that.
Luis?
No.
Does anyone, Luis, are you able to answer? Maybe
the algorithms that we use 6 different algorithms when we were testing which ones we should use. We came to the conclusion that random forests and neural networks were the one that were giving us better results. All this work from Petrus used neural networks. For other type of work, for example, on liquefaction, random forests was the algorithm that we used. But I don't know if you're mentioning some specific type of algorithm that I've not heard yet.
I wonder, I also have only tried with deep learning, basically an extended neural network myself. Evolution, maybe the person that typed the question may add something else? Because
Give some more details, yeah.
Yeah.
So if you'd like to give more details, Yusuf, let us know if we've answered your question or not. And that's, I think, right. Oh, I think I understood. If random foresting is used, it might be different than what I thought. They say. Okay, at the moment, there's no other questions. So unless anything comes through in the next 30 seconds or so, I think we could wrap up this this webinar. Any final thoughts from Luis, Martina, Vita? Anything you forgot to say that you want to add? We're good? We're good. So thanks to everyone for attending. And as you know, this is being recorded. So we'll send out an email to all of the registered participants with a link to where we're going to put this video up, links. We may probably put it up, I think, on the EFEHR YouTube. GEM maybe will put it on their website, but wait for that email. If you want, do follow us on our social networks, Twitter, LinkedIn. That's good places where we will also update you when these videos are available. So yeah, and if you do want to contact us, you know how to contact us, and just let us know if you have any additional questions. Thanks, everyone.
Thank you.